So as Porrick showed us, Hadamard proved in the late 19th century that if you have a matrix with complex entries of modulus 1, then its determinant is bounded above by n to the n over 2. And this upper bound is met if and only if M conjugate transpose is n times the identity, right? So as an example, character tables of abelian groups give you a Hadamard matrix at every possible order. So you would like to study a more restricted set of entries where the problem becomes more interesting. So in the real case, plus minus 1 entries, those are the real Hadamard matrices, and they're only met at orders 1, 2, or multiples of 4, possibly, right? Yeah, the Hadamard conjecture says that this is always achieved at every possible multiple of 4. You will find a Hadamard matrix. But Hadamard also posed the maximal determinant problem, which was for a real matrix plus minus 1s, what is the maximal determinant at every possible order? So here I have some examples of maximal determinant matrices. And I want you to look at this one. The 5x5 case satisfies this equation for the Gram matrix. It's 5s along the diagonal and 1s everywhere else. And here is an account of all upper bounds that we have for the plus minus 1 cases. In historical order, first Hadamard, for all n, you have this bound. Then you can strengthen that for n odd, which is the Barbour bound. It has this shape. But this is only achievable when n is congruent to 1 modulo 4. And in particular, when this is a square, which is equivalent to n being a sum of consecutive squares. Then Porrick told you about the Elish-Voitas bound, which is the even non-Hadamard order case. And the Elish bound, which there's still no examples of any matrix achieving this. So let's focus on this talk on the Barbour bound, which for the plus minus 1 case applies when n is congruent to 1. So let me give you this determinant lemma. If you have a positive definite Hermitian matrix where the of this column, let's say, satisfies that the absolute value of these entries is bounded below by 1, and here I have m's along the diagonal and a 1 here, then its determinant is bounded above by m minus 1 to the k minus 1. K is the size of the matrix. So you prove this by elementary row operations and then applying Fisher's inequality or Hadamard's inequality on the product of diagonal entries. I'm not going to go through the proof, but I'm going to use this as a lemma that to prove a generalized Barbour bound. So here, if we have G, which is going to be our candidate Gram matrix, being positive definite Hermitian with diagonal entries equal to m, and the off-diagonal entries are bounded below by 1 in modulus, then you have this determinant bound. And well, in the end, we're going to substitute here m equals to n, because that's what will happen when the entries of our matrix m has modulus 1, the entries. So this will give us the Barbour bound. So to prove it, we just do an induction argument. We start with our positive definite Hermitian matrix. Then we use linearity and separate what we had before into 2 determinants. This is of the shape that we had in our lemma. And all of these are bounded below by 1 in modulus. So we can apply that lemma. And then we have this matrix, which is of size 1 less, right? It's of size n minus 1. So we can apply an induction argument, and we obtain the result. Now we just need to prove the base case. And the base case is just the direct computation, where you have an element of modulus bounded below by 1. So you have the determinant is this, which has the right shape. So as I said, if we substitute m equals n, then we obtain that if you have a matrix with complex entries of modulus 1, which does not achieve the Barbour bound, the Hadamard bound, right? If the off-diagonal entries of its Gram matrix are bounded below the off-diagonal entries by 1, then you have this bound. And this is achievable if and only if you satisfy this Gram matrix equation, in which you have n's on the diagonal and 1's off the diagonal, right? This type of matrix, which we already saw in the 5x5 case. So in the real case, we can characterize the matrices that have constant row sum that achieve this bound. And it turns out that if you have constant row sum and you satisfy that Gram matrix equality, then you are the ±1 incidence matrix of a symmetric design with these parameters, which Brouwer showed to exist when T is a prime odd prime power. So it's still always for sums of consecutive squares, but we just know it for now for sums of consecutive squares of prime power. So now let's look at this problem over more general setting, more general set of entries. So we can look at complex roots of unity. So root of unity is just a complex number whose kth power is 1. And since the entries form a multiplicative group, then you know that the off-diagonal entries of the Gram matrix are going to be sums of roots of unity. So then the condition that you want to have the Barbour bound to apply in this setting is that the modulus of the sums of kth roots of unity is always bounded below by 1. So this is just having the roots to form a lattice. So we would have to be looking at fourth roots or third roots, which is what we're going to focus here. Porrick already told you a little bit about the sixth roots, which also applies. So let me first tell you a little bit about Butson-Hadamard matrices. Butson-Hadamard matrices are matrices with entries in the kth roots of unity, and you know that BH and K. So it is known that when K is a prime number, then you have existence at orders 2 to the m times p to the n, where m is less or equal than n. Right. So for a BHN4 to exist in the fourth roots of unity case, then it is necessary that n is even to have vanishing sum of roots. Right? Here are some examples. And there's a conjecture, I think it's by Seberg, that they always exist at even orders. Right. It's still unproven. Yeah. It actually is stronger than the Hadamard conjecture. Yeah, and I'm going to tell you about it now because there's this Turin morphism by which if I write my complex Hadamard matrix, my phase 4 Hadamard matrix in this shape, then if I arrange it in this way, then I get a real Hadamard matrix, right? So there you go. The existence of BHN4s at every even order implies the Hadamard conjecture. So Porrick already told you about this type of matrices. These are maximal determinant matrices at even orders that are not a multiple of 4. And I'm going to call them EW matrix because they achieve the Ehrlich-Voitas bound. And they satisfy this Gram matrix equation. So there you go. This is what I just said. Kohn showed in 1986, he was the first person to consider the maximal determinant problem over a larger set of entries than ±1. He considered the complex case. And he shows that the existence of a Barbour matrix of odd order in the fourth root of unity is equivalent to the existence of an EW matrix of skew type. So having this shape, it's got blocks of half the size, and then you have same here, and then a -1 there. And actually, the construction that Spence gave for Ehrlich-Voitas matrices, EW matrices, can be put into the skew type form. In particular, if you have here to be circulant, blocks that are circulant, then you can also convert it into a skew type. So if you apply that, if you pull this up, I'm going to divide here by 2, and I get an order q squared plus q plus 1 for the complex matrix. Right, so we have 2 constructions achieving the Barbour bound for the 4th roots. One, when n is congruent to 1 mod 4, which is just the real Barbour matrices that we consider as complex matrices, plus minus 1, plus minus I. And then we have the Spence construction, which is at orders q squared plus q plus 1, which is 3 mod 4 for an odd prime. And in fact, the other construction for the real congruent to 2 mod 4 matrices is just from doubling this one in the sense of the Turing morphism. All right, so now let's consider the 3rd roots, which it's probably the most interesting case because you don't have, in this case, you don't have anything from the real world, like pulling up to your maximal determinants. So, right. In this case, BHN3s can only exist when n is a multiple of 3. This is different than when n is when it's BHN6, because with 6 you can have cancellations at other orders. So this really is just for multiples of 3. Tau? I don't know. This one is just the quadratic residues in the core, modulo 5, and you border it. Yeah. So, okay, just an overview. As upper bounds, we have the Hadamard bound, which still applies. And then we have the generalized Barbour bound at orders 1 or 2 mod 3. But the Barbour bound, the generalized Barbour bound can only be met at orders 1 mod 3. And as lower bounds, we have, well, the Hadamard bound existence constructions in orders 2m times 3 to the n. And then we will show that we have actually infinite families achieving at least 1 over square root of 2 of the Barbour bound when n grows larger, right? So let's look at the first result. If you have a BHN3, if it exists, then there is a matrix M over the 3rd roots at order n squared plus 1, which is 1 modulo 3, having determinant at least this, which is a fraction of 1 over the square root of 2 of the generalized Barbour bound when n goes to infinity. And the way you do is just combining 2 results. What you're going to do is you're going to border a constant row sum complex Hadamard matrix. And if you do that, then the determinant is bounded below by this quantity. And if you just remember what the Barbour bound is, and you take quotients, this approaches 1 over the square root of 2. Right, so the only thing that you would need is BHN with constant row sum to plug in there. So turns out that the Bush construction, given any BHN3 will give you 1 of the square of its size with constant row sum. So you apply it, we just substitute in our previous theorem n with n squared, and there you go. And now for orders which are 2 modulo 3, what we have is that if you have a prime power, an odd prime power congruent to 1 modulo 3, then there is a matrix of size 1 plus, which then it would be congruent to 2 modulo 3, over the 3rd roots, such that its determinant is at least q to the q plus 1 over 2, which compared to the Barbour bound in that order also approaches 1 over the square root of 2 as q goes to infinity. So the way you do it is you take the set of cubes in the finite field with q elements, and you take, well, in the units of this field, and then you take its cosets, and you build a matrix which is going to be indexed by elements of the finite field. And then you're going to assign it the value omega to the k if the difference of the row and column entries is in the kth coset. Right? And then you border it in this way, and you get a generalized conference matrix, which will have determinant q to the q plus 1 over 2, which then, if you compare to the Barbour bound in this order, you see that it approaches 1 over square root 2, right? And here we have zeros, but we can always change the entries one by one without decreasing the determinant, so the bound still holds. So to see a particular example, take p equals 7. The cubes are plus 1 and minus 1, 1 and 6, and these are the cosets. So you create this matrix, where here I got 1 and 6. So these are given ones, and then omega squared for this coset and omega for this other coset. And then I border it. And this matrix has large determinant. OK. We looked also at structured matrices that achieve the Barbour bound. And the first thing that you can do is, OK, what happens if I have 2 entries? If you have 2 distinct entries, that could be 1 and omega. And if you're meeting the Barbour bound, then it turns out that you have that the entries where you put the omegas are the incidence matrix of a symmetric VK lambda design with this constraint on the parameters. And there's only finitely many of these. It's similar to what we had with the infinite Barbour bound family with the Brouwer construction. But in this case, just the Diophantine equation has only finitely many solutions. And then you get to, this is trivial design, and here is the projective plane. And you can do the same for strongly regular graphs, which are graphs that have are regular. Any 2 adjacent vertices have the same number of common neighbors. Any 2 non-adjacent vertices have also the same number of common neighbors. So again, you obtain some constraints that only give you finitely many examples. One is the Peterson graph, and the other is the Paley graph at orders 13. Right? Here they are. And if you just decorate the matrix with ones on the diagonal and then omegas on the adjacency matrices, omega squares in the complement, then you obtain 2 examples of Barbour matrices. So we got, to sum up, we got Barbour matrices up to order 13. Order 16 is not achievable by the same obstructions, number theoretical constructions on norms on the third roots of unity. And then, so the next open case would be 19. And we have this little table of some results where we got large determinant matrices. To prove maximality of this, it involves computational methods. We have it for sure for 5. For 8, we're pretty confident that that's the maximal determinant value. And yeah, also we have a very good matrix for the 15, but again, it's hard to check if it's actually a maximal determinant matrix. It would be interesting to like complete this table a little bit more. And yeah, and then we have some results of existence of BHN3s, but not nearly, it's not nearly satisfactory. You would hope to have more constructions for that. And then we have some lower bounds at orders 1 and 2 modulo 3, which are achieved infinitely often. Okay. Yeah, so some questions that I can leave you with, like, can you find more infinite families of BHN3s? And perhaps an infinite family of Barbour matrices over the third roots? And this seems really interesting to me because for those cases where you don't have existence of Barbour matrices, of Hadamard matrices, what is the maximal determinant? Right, those that come from number theoretical obstruction. And it would also be interesting to study the equivalence of these matrices and see if the examples that we have are unique up to equivalence. So yeah, that's it. Thank you very much.